Well, I'm just getting done with a long holiday weekend, a whole bunch of days off, and been pretty productive with that, I guess you could say. But well, actually, look at that. That's a whole bunch of stuff, whole bunch of different boards. I'm actually running out of boards, so I'm gonna have to tear some of this stuff down. Before I do, I want to document what these things do and how I got there and all of that kind of stuff. Through my foray in electronics stuff so far been mostly just following different schematics and what all, and you just slap all this stuff together, the thing works. Well, that's all good, I guess. But like, look at all those like chips and stuff in there. What do those things do? Like, well, it's all good if you just throw one of those in there. You need that. Well, what does it do? And a lot of the like tutorials, I guess, don't really go into that too much. And I really want to get down to the nuts and bolts of, what does this thing do? Like, you give it some input, you get some output, but what's going on there exactly? And well, all those kind of chips like that run off of digital logic, ones and zeros, for lack of a better way to put it. And so I thought it would be best to get right down to the nuts and bolts of digital logic. That way, it's all good if you get that thing right the first time, but if you don't, you need to diagnose the problem. It would be good to actually know what's going on under the hood, so to speak, with these chips and stuff like that. So, the basics of digital logic. It's really about, you get some kind of input and you do something with it and then you get an output. The probably most simple logic circuit here, and all of these are called gates. These are the most bare bone parts that everything else is made out of. And the simplest one is the NOT gate, or it's also called an inverter. And this is the symbol for it here in schematics. You'll see something like this. And actually, this is a schematic for a diode. That's what this triangle part is here. And it just indicates that the current is flowing, well, from left to right in this case. The circle part is the NOT gate itself, or the inverter. So you'll often see these where there might be some other symbol here, and this little circle that's on the end tells you that whatever this gate is doing, that you're going to invert the results. So if this gate would give us a 1, we're going to turn that into a 0. If this gate would give us a 0, we're going to turn it into a 1. And I didn't do a very good job drawing this in my notes here. Actually, the other ones coming up next are done a little better. But so basically, what I'm saying here is I got this little truth table here. Ignore everything to the right of this for a second. So if my input is a 1, I expect to get, or a 0, that is, I expect to get a 1 out. Or likewise, if my input is a 1, then I expect to get a 0 out. And this is actually a circuit diagram that will do that. This Circle K thing looking guy here in the middle is probably your most basic run-of-the-mill transistor. One of these guys right here. There are a bunch of different kinds, but this is probably the most simple one. Garden variety type of thing that you'll come across. They're very common and cheap, and they will work just fine for this. So the idea here is, again, like our input is this part here, So if we give this, remember this is a transistor, so if we give this thing power, it'll turn the transistor on and current will flow from the collector here to the emitter, straight down. If this is off, no current will flow this way, so it has no choice but to go this other way. So that would, anytime that we have a 0 here, no current, then this thing will be on. It'll be getting power this way. If we turn the transistor on, that's going to let current go through here. So it's not going to go the long way around because it always wants to take the shortest path of least resistance. So it's going to go straight down. So this thing will be off then. That is an inverter. We have other kinds of logic gates that are kind of like that. This one is the AND gate. And that's what you would see in a schematic for that. You've got your A and B inputs and then one output here. And what we're saying here is, if A is 0 and B is 0, we're going to get a 0 because we're not putting any power through this thing at all. If one or the other, that's what both of these guys are. If A is 0 and B is 1, we're still going to be 0 because we want AND. So AND means, A is 1 and B is 1. And we see that down here. If A is 1 and B is 1, we'll output a 1. Both of those have to be on in order to get our 1 out. Okay, so both of these inputs need to be on to get a 1 out of here. Anything else, a 0 will be coming out of this gate. And this is the schematic for it. Again, it's a couple of transistors, and they're actually hooked up here in a series. And so what happens is, if we give power to just this one, we'll let it go through this way, but that's as far as it's going to go, which means then this current will just keep going that way. Or likewise, works the same way on this other one. So if this one's on and this one's on, straight out here, so that will give you the desired result for that. So both inputs have to be on to get a 1 out of it. So that's what our truth table says for this guy. Another type of gate is an OR gate. And this one we're saying if A is on or B is on, then turn this guy on. And this is the truth table for that. So neither A or B is on, you're not going to get on your output, you're going to get off. If A is off but B is on, you'll get an on because one of those is on. Likewise here. And then at the bottom here too, if both of them are on, you'll still get a 1. Because one of the two is on. Actually, in this case, both of them are on. We'll get to why I got this C XOR thing here in a second. And that's the schematic down here for that. It's still transistors, but in this time, they're in parallel instead of a series. So, if A is turned on, current will go bloop down through here. Or likewise, if this one's turned down, it'll go bloop down here. If neither one of them is on, then you're going to get a different result. So that's pretty much what's going on with those guys. We'll see about this here in a second, though. Turn the page for that one. And so that brings us to the XOR gate, which is the last one of these. And with the OR gates, if we had both of them on, you would still get a 1. But what if I want to say, I want to know if one or the other is on, but not both? And that's what an XOR gate is. This is the only difference between an XOR gate and an OR gate is right down here at the bottom here. On the OR gate, if A and B are on, you'd get a 1. With an XOR gate, you'll get a 0. Because we are specifically saying about one or the other, but not both. Where the OR gate doesn't care about that. As long as one of these is on, it'll give you a 1. And, this is the schematic for diagram of that, or symbol, rather. The diagram for it is down here. And what it is this is a combination of an AND gate, a NOT gate, or an inverter, and then this thing here is an OR. So it just smashed together the last 3 gates we talked about. And it does so in such a way, like if A and B are both on, that's going to give an on here. And we're going to invert that, which will shut this whole thing off and shut this whole thing down. Because, if A and B are both 1, we want a 0. So that will just shut everything off if A and B are both on. If they aren't, if only one or the other is, that'll go to this OR gate and it will just verify that one or the other is on. Notice that the AND gate here and the OR gate here, they both get A and B inputs. These are the same A and B inputs. And so, like I wrote here, this is maybe better thought of as not and then OR, because this thing here, this part's the and, this is the not. So this whole thing I've got circled in purple is called a NAND gate, or basically not and. So we've just inverted the results of the AND gate. That's what this thing is doing right here. And then we're feeding that to the rest of the circuits. So that's what's going on with all of that. And I went ahead and built these so that you can see how that actually works in action. And it might make a little more sense to see it in action rather than me describing it maybe poorly. So we'll power this up. This guy is just power. And we'll talk about this thing in a second, but right here is our inverter that we talked about earlier. So I'm not giving any power to the transistor, so we're feeding it a 0 and we're getting out a 1, meaning the LED's lit up. So if I click on this, I will be feeding power to the transistor, feeding it a 1, and we get a 0 as output. So that's how that works. Okay, so that's literally just built up what we had and we saw in diagrams like this earlier. This is a physical representation of that. This one over here is an AND gate, and it's built up just the same way as our schematic showed. And so if I press one button, nothing happens. Press the other, nothing happens. Press them both, A and B, then we get our outputs of 1. Anything else gives us a 0 off. This one is an OR gate. So if I press A, lights up, or B, lights up, or both, lights up. So this is an OR gate, AND gate, and our NOT gate, or inverter. This guy over here is an XOR gate, and I purposely made this as compact and pretty much incomprehensible as you can think of. I wanted to see how small I could make this, because you can see just the AND gate here or the OR gate, they take up an okay amount of spot. And like I said, the XOR gate takes all 3 of these things and smashes them together. And that's what we've got here. That's what this thing is. And it works how you might think it would. So, one's on, the other's on. And what we're saying here, again, remember, if one or the other is on, we should get a 1. If both of them are off, which they are, we should get a 0, which we do. But if both of them are on, we want to get a 0 here. So let's check that again. So, oops, these are a little wiggly. There we go. A, B, neither A nor B, that's just off, and both, it should shut off, which it does. So that's digital logic at its, I don't know, what would you call it? Most basic level, I suppose. And understanding these helps you understand that this chip is an inverter chip. It has a whole bunch, actually 6, inverter circuits right on it that do exactly the same thing as this does. And you can look over here. I got all kinds of different chips. Every single one of these does different things. We've got NAND gates, NOR gates, inverters, and or XOR, etc. And one thing I should mention, though, I talked about it kind of in a little earlier, is that you can have the inverted of each of those gates we just talked about. And it's literally just an inverter tied to the end of an AND gate, an OR gate, or an XOR gate. So you can invert all those outputs too, and they have chips that do that as well. So not only are they an AND gate, but they've got a built-in inverter, which makes it NAND. So that's all that's going on there. And this one I'm not actually going to break down. I'm going to keep this because I especially like this XOR circuit. This would be a monstrosity if I just kind of let it spew out like all of this, since it is all of these things together. That I'm actually kind of proud of, to get that squished down quite as small as I did. And to think that you can have 4 of those circuits on something as small as this, which is not big at all. This is just, see, look, it's pretty small. But that's all for this one.